So bisection, the logic is pretty clear. Another technique in the same family is called the secant method. Here's one of the ideas, graphically. If I have my function going like this, and I have my a, and I have my b, and I check c, well, c is so close to the root, and I know it's close to the root because the function value is so small. Why would bisection is just going to ignore that. It's going to say it's negative. I don't care. I'm just going to keep bisecting over here. And in fact, it's probably going to keep bisecting like this for quite a number of times until it gets to closer to the root. And that just seems inelegant. It seems like we're wasting information because we know the function value. We know how far are we from 0 vertically. We're calculating that anyway. So why not take advantage of it and use it somehow? So here's what we're going to do instead. We're going to go from what's essentially a constant idea to something that's linear. So it's going to be a little different in flavor, but it's going to still have an a, a b, and a c. A and b are our current guesses to where the root is, and c is going to be our new guess. So what we're going to do is connect the function value at a and b with a straight line. And our c value, in this case it doesn't turn out to be that great, but our c value is going to be where that crosses the axis. Okay? So basically we're assuming our function's close to linear. And if it is, then the straight line that we just drew will be close to where the function actually crosses the axis. And then we'll keep doing that over and over again because it's not going to be perfect on the first iteration. So this is the thing here. Pretend our function is linear. Connect the dots. Find c, the root of the line, defined by those 2 points. And we're going to include that in our updated coordinates. So what we're going to do is start at 2 values here. A2, B4 looks better on the overheads here. It's about 4.5, and here. Now, if that's my new A3 and B3, and we follow that straight line down to the axis, that's almost right on top of the root. And you can tell, I hope a little bit why. The graph curves a lot. When I start zooming in, courtesy of calculus, everything starts looking like a straight line. And because we're assuming, by following a straight line, that our graph is close to a straight line, as soon as we start getting in the region of the root, we're going to get something that really converges quickly, because our line and the actual graph line are going to get more and more similar. It's a nice limiting thing. Let me actually just do the last one here. So if we did this, we'd throw A3, call that A4, call that B4, and that line is almost going to be on top of the root. Oops. One last try. There we go. C4. So it might jump around a bit at the beginning, but it's going to zoom in pretty quick once we get into the ballpark. Questions or comments about the idea or the concept behind that? What does it look like when we actually compute this? How do we actually do this calculation? So I was drawing it, but how do we actually calculate the root, knowing that we've got a point A and a point f of A, and say B and f of B. And what we're trying to do is connect those two dots, get down to here and find C. Well, before we can find the root, we better find a formula for that line. We've got an m in here. And the slope is your change in f over your change in x. And that's f of b minus f of a, that's the difference, over b minus a. Fantastic. So, excellent. M is in there. Let me throw in the one that's nicer. Some people like going for intercepts first, but let me show you this one, because it should look also familiar. Tangent line. Except there we had f prime of a. F prime of a, x minus a plus f of a. That was the tangent line formula. Here we're doing something very similar, except we don't have a derivative, so we're estimating the slope using a different technique. But it's the same idea. All right, that's the line. Is defined by this. So it's a line through the point a, f of a, and it has slope m. We'll do m as a little side calculation here. Change in y, change in x. And then we're going to solve for the x for c, which is equal to the x value when y equals 0. because we want to find the root. So we plug in y equals 0 and solve for x. And this time, it's a linear equation, so we are guaranteed that we can actually solve that. So we're going to have 0 equals m, call the x coordinate now c, plus f of a, minus f of a equals m. Cross the m off, put it over here. And then we're going to bring the a over. So we'll have a minus f of a over m equals c. That is our alternative to the bisection formula now. And now we can run our code. We can write our secant function. All right. Bisection is very similar, so what we're going to do is take all the code from bisection and put it in a new file, but we're going to call it secant without the caps. All right. And we will save it, again, as secant.m. Okay. So everything at the start is fine. I need a function. I need an a and a b, 2 starting points. I need a tolerance. That's all good. I want to continue while the tolerance is what it is. This gets a little different. So find the root of the point through a f of a and b f of b. All right. So that we said in 2 different ways. It was f of b, let's get rid of all that, minus f of a divided by b minus a. That's the slope. And then we said c was going to be a minus f of a over m. That is all the math we just said, written in MATLAB, ready to go. Even better, we don't have to do any of this sign junk anymore. We're taking a leap of faith that this is going to work, that following the straight line over and over again, rebuilding the straight line, following the new one, that process is going to get us to the root. And so all we have to do is replace our a becomes our new b value. So update the a, b values. And b is the new value we found that was c. So we throw away the old a because it's being overwritten. This takes a little bit of mental gymnastics at first. I don't want the old a value, so I'm going to replace the a with what b is. I don't want the old b value. I want it to be what I just found, my new value, which is c. And that's secant right there. All right. Now we'd like to test this. So I'm going to show you 2 testing methods. One is with the function that we actually had before here. So just going back one step. This represented an equation like this, but I wrote it out as a function of e to the x over 2 minus x minus 10. That is the function that is graphed here. And the reason I want to have that graph is because I know the answer should be around 5.5. So we should get an answer. I think it looks a little bit below 5.5 if we use that function. And here's how we would do that in MATLAB. We're going to make a W43, solve e to the x over 2 minus x minus equals x plus 10, I think. Yeah. That's not quite right. Let me just go double check. Yeah, OK, that is right. Fantastic. We want our function equal to 0. So exactly the same syntax we had before. We're going to put an ampersand out front, ampersand x. So it's a function of x. It'll take x's in. I'm building a little kiosk that's waiting for one input. And the way you do exponentials in MATLAB or e to the base is just exp minus x minus 10. And we literally copy that into a function. W44, I think. There we go. And then we say, hey, let's run secant on that. F. We started in the first example at 2 and 4. 2, 4 are our original guesses. And let's take the semicolon off so we'll see the output. So this is as simple as it gets. What do I want to find the root of? F. What does secant do? Find the root. Go ahead and find the root. So we're going to run that and see what happens. Run. Lovely. Is that number reasonable? Does it make any sense whatsoever? I'm getting 5.47. I'm ecstatic by this, and I'm hoping you all will be once you realize. Let's go back to the graph. This function came from, or is equivalent to, this graph. Where is the root on this graph? Near 5 point something? Around 5.5? Lovely. So what secant has done has honed in on that root, and it's telling us, no, it's not 5.5 actually, it's 5.479. So very close to that, and much more accurate than we could ever get with that diagramming approach that we did visually. So it's doing that solving for us, and we can actually see how quickly it's doing it just by a quick removal of a semicolon here. I'm just going to see what the C values are. We're going to print the C values every time, and we see that it actually doesn't take that many iterations. Then we go back to 4.7, and then we hone in very quickly. Like these last three things are the same to 2 digits after the decimal. And once we've honed in, we've satisfied our tolerance and we stop. So that's good stuff. Because if you look at the two functions, secant and bisection, they take exactly the same inputs and do the same job. They find the roots of the function, starting at a and b and with a certain tolerance. So that means when we go back to our code that was finding the angle of launch, we can literally write the same code to find the optimal angle or the angle that hits our target, but just change the name of the function that's going to do the searching for us. Bisection and secant are interchangeable because we wrote them that way. They do the same task, and we wrote them so they took the same inputs in the same order. And so we can run and verify that, in fact, our secant algorithm gives us the same values that we got before, 62.41 degrees. Little different, not quite the same after you get to these digits down here, but that's because we didn't set the tolerance very fine. But it does the same job. But we've basically built an interchangeable element that does the same job. What I will say, just as a brief note about this, is if you want high precision answers, the secant method is much better for super precise. If you want to get down to 10 digits, secant will do that faster because of that straight line approximation being a little more informed than just the am I positive or am I negative relative to the root. Both of these are unimaginably better than trying to mess around with loops. I swear if I see loops for solving equations, I'm going to scream. Because, look, once you've written them, this code doesn't get any easier. I read this as, find me the roots of the function f starting at these guys, and I want my answer to 0.01 accuracy. It doesn't get much simpler than that. Even writing the loop and thinking, what should I start and end at, is more complicated than using this function that we've built.